just did. All right. Guys, that was Maddox speaking, just so you know. Okay? We're going to talk about inductive reasoning. So these are basically ways that we think through things. Okay? Inductive reasoning is the first one we're looking at. We have a little example here. It says, use the pattern of figures below to determine the missing parts. So we have a series of shapes, but we also have a series of patterns. The first question says, what is the shape of the 8th figure? So we actually only have 7 figures here. What would the 8th one look like? Audrey, what do you think? It's a pentagon. I would agree. Pentagon. See if I can draw a really bad pentagon here. Okay? Hey, don't judge. And then what would be the next shape? Do we know? Somebody else? Nicole? Circle. Be a circle. And then a square, and then back to a pentagon and a circle. That's the pattern, right, for the shapes. So this would be the 8th shape would be a pentagon. What is the design of the 16th figure? So let's look at the designs really quickly. We have, in this first shape, we have, I would call it maybe a solid. Okay, it's filled in completely. The second one is checkered. Looks like chicken. Checkered. The third one is a grid pattern. The fourth one is stripes. And then the 5th one is back to solid, and it repeats itself, doesn't it? So solid, checkered, grid, stripes. Solid, checkered, grid, stripes. And then the circle would be solid. And then we're assuming it would just keep going, wouldn't it? So every 4th shape, it goes 4 shapes, and then we start the pattern over again. So what do you think would happen on the 16th one?
Grid.
Stripes. Look. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We should be back at stripes. Another way to tell is that 16 is divisible by 4, isn't it? And it's in chunks of 4. So if we just divide 16 by 4, that ended up evenly, we should be at the last one. Number 3, what's the shape of the 24th figure? So the shapes change after how many? 3. We have a square, a pentagon, and a circle. That's 3. And then it starts square, pentagon, and circle again. So what do you think would be the shape of the 24th? A circle. Yeah? Because 24 divided by 3 is 8. It goes in there evenly, doesn't it? So I would assume that that is a circle. That does not look like the word circle. And the 4th one, what is the design of the 30th figure? Remember, design is how many? Gentry, what do you think? Think it's checkered? Okay. I would agree. The 30th, so we know we have every 4, we have a design change, don't we? So 30 divided by 4 is 7 with 2 left over. So I go back to the beginning and I just count 1, 2, and I'm back at the checkered one. What we did was called inductive reasoning. We looked at the pattern of things that happened and assumed that that was going to continue, right? And based on that, then we said, here's what would happen. When you make observations, are your observations always true? No. We do that, unfortunately, sometimes with people, right? We don't really know them, but we make some observations about them, make some assumptions, and then say, oh, well, this is true about them. Is that always the case? No, kind of dangerous. Kind of dangerous here too. But are we going to stop? Probably stop making observations? No, that's one of the ways that we do problem solve. That's pretty normal. Inductive reasoning is where we look at a pattern and we determine what's going to happen in the future, or what we think could happen. So let me get the words right here. Inductive reasoning is a type of reasoning used when a pattern, example, or a past event leads you to draw a conclusion. Okay? Not facts, but just what we've seen. A conjecture, so when we draw a conclusion, that conclusion that we're drawing is called a conjecture. A conjecture is an unproven statement based on observations. So we've observed this happening, we've observed this pattern or this shape change, and now we're going to make a statement about what we think will happen in the future. And then a counterexample, that's a very specific example. So a specific example that proves a conjecture is false. So I might make a statement about something and I say, well, this is what I think is going to happen. If you can give me one example of it not happening, then that is a counterexample, and you can say, well, that's great, Ms. Bradfield, but you're wrong because this happened. This can happen. And then you have proven that I'm false, that my statement is false. But that's how we disprove something that a conjecture that comes across through inductive reasoning is by giving a counterexample. We're just going to look at a couple of these. It says, what are the next two terms in the sequence? What are the next two terms in the sequence? So number one, what's happening in the problem, Audrey?
It's like adding by 2 and adding by 4, adding by like, and then you add 2.
Okay, add 2. This one's add 4,
6.
add 6. So the amount that we're adding is increasing by 2.
Yeah.
Okay. Plus 8. So the next one would be
37.
plus 10, which would give us 37. And then the next one would be plus 12, which would give us 49. Okay, as long as that actually continues to be what happens. Could I switch it up and give you a list of numbers that doesn't continue that way? Yeah, what if I made my list of numbers and they all of a sudden they went the other direction? Is that possible? So we used inductive reasoning to come up with our next problems because we don't really know what the sequence is. We're just basing it on what we have observed. Ooh, how about number 3? We have 108, 36, 12, 4. 4/3. Let's find somebody that hasn't spoken yet. You've just spoken. Come on, let's share the love, guys. What do we think? What happens? How did we get, can we recognize any of these that might have happened? Chris? Minus 7?
We're on 3.
Oh, yeah, we're on 3. I think you probably would have grabbed that one pretty quickly. Anna? Divide by 3. Would you agree? Okay. May not recognize it right away with 108, but 108 divided by 3 is 36. So divide by 3. gives me 36. Divide by 3 gives me 12. Divide by 3 gives me 4. Divide by 3 is 4/3. They just left it, right?
What's 4/3?
So the next one would be 4/3 divided by 3. Dividing by 3 is the same as multiplying by 1/3. So I would say times 1/3. What is 4/3 times 1/3? This is not a trick question. We just multiply across. 4/9. So we just go that way, multiply across. Then we're going to do it again. Times 1/3. What would that be? 4/27. There we go. Again, could have changed. We don't know for sure, but we think that that's what should happen. Number 4, if the following pattern continues, how many triangles will be in the 6th polygon? All right, let's talk about this a little bit. We've got some polygons here. What is this called? The first one called? A triangle. And so how many sides does the triangle have? 3. How many triangles do you see there? 1. The second figure is a square. How many sides does it have? 4. Now what they've done is they've drawn in a diagonal. A diagonal goes from a vertex, so a corner, to a non-adjacent corner or vertex. Adjacent would be right next to it. So if we go right next to the one that we started from, that would just be another side of the figure. So they drew a diagonal in. When they drew one diagonal in, how many triangles did it make? 2. What's the third figure? How many sides does it have? 5. It's called a what? A pentagon. And how many triangles were drawn in that one? 3. The fourth figure is a, how many sides does it have? 6. What is that called? A hexagon. How many triangles do I have on that one? 4. How many sides would I expect the next one to have? 7 sides. And how many triangles do you think there would be? 5. And the 6th one would have how many sides? 8 sides, which is a octagon. How many triangles do you think it would have? 6. So 6 triangles in an octagon. All right. So we're going to carry this problem over to the next question. So the next question has to do with this problem right here. What conjecture can you make about the number of triangles formed by connecting one vertex with the remaining vertices of the polygon within number of sides? So it's just asking us, like we just did, to compare the number of sides to the number of triangles. So let's put it in table form. This was the number of sides. A lot of times when we do stuff with sides of polygons or whatever, we put an n. So I'm going to say that an n represents the number of sides. And then the result was the number of triangles we have. All right, so when we had 3 sides, then we had 4, 5, 6, 7, and so forth, right? When we had 3 sides, how many triangles did we have? 1. When we had 4 sides, how many triangles did it make? 2. And 5 sides? 3. 6 sides? 4. 7 sides? 5. And we know that 8 sides was 6. It's asking us what's the pattern here? What do we notice about what's given and the number of triangles? How could we figure out what happens? Bella?
The amount of triangles goes up by 2,
Okay, so let's start with the number of sides. If I'm given a certain number of sides, let's say I have something with 20 sides, how many triangles would there be? 18. How did you get that? You subtracted 2. So what we can see from the pattern is that the number of triangles equals the number of sides, right? Which is n minus 2. So we just made, that's our conjecture, that the number of sides minus 2 is equal to the number of triangles. That seems to be what's happening, doesn't it? Do we know for sure? But I'm pretty certain on this one. Pretty certain. Feeling pretty good. But could be true, could be false. We don't know. Number 6, based on the data in the table, how many students will earn a scholarship? This is kind of a tricky one, so I'm going to do this with you, like pretty closely, so pay attention. Because if I look at the data and I look at the number of students, is it pretty consistent or is it up and down? Up and down. So it's kind of hard to tell, am I adding or subtracting something? So we're going to take this a little bit logically. Because the number of students change compared to the number of scholarships earned, the thing that would be consistent would be a percentage. A percentage would be consistent. We could have a small pool or we could have a large pool and still apply the same percentage to each, right? Okay, so let's look at it like a percentage. What I'm going to do is I'm going to take the number of scholarships earned from the number of student athletes, and I'm going to find out what percent that is. So 196 out of the total is 854. And I'm going to see how much that is. We'll get our handy dandy calculators out, and I'm going to take 196 divided by 854. I'm going to go out a bunch of decimal places. It's about 0.22951 or 22.951%. Okay. I'm just making a percentage. I divided it and converted that to a decimal, but it comes out to a lot of places, so I just rounded. When we're applying a decimal or a percentage, we want to go out several places. The more place values we go out, the more accurate our answer will be. That's why I did that. Okay? But it's roughly 23%, yes? If we were to really round. All right, let's see if for everything that the scholarships earned is actually about 23% of the number of athletes. Let's test it out. So we're going to test it on the other ones. I'm going to take 725. This is number 2. I'm going to take 725 and I'm going to multiply that by my decimal, which is my percent. 0.22951. And let's see if I get close to 166. If I get close to 166, we're going to start to feel pretty good at it. 0.22 times 951. If I round this up to the nearest whole number, it gives me about 166. Does that check with what we got in our table? Yes. Boop. All right. How about number 3? Let's try number 3. We're going to use, this time, the number of student athletes was 816. We're still going to use our 0.22951 that we had from our original piece of data and see if it gives us about 189.
Wait, why did we make it a percentage?
Well, whenever we find the percent of something, we always change it to multiply and change it to a decimal. So I'm really finding out what about 23% of it is. But I have to change it to a decimal to get that. Okay? So I'm taking for number 2, I took 725 and I basically multiplied it by approximately 23%. But as a decimal, it's 0.22951. We just scoot that decimal over 2 places, right to the left, and we're right back to that decimal. So when we use the percent, we have to use the decimal form of it. What is 861 or 816 times 0.22951? What is that? Okay, so 187, is that pretty close to 189? That is really close. There's some variables that could happen there. If it's pretty close, it's a keeper. All right, how about number 4? Let's try that. 948, we're gonna multiply by the same thing, right? We're applying that same percent to it. What do we get for that one? If we round to the nearest whole number. 218? Oh my goodness, it's the same, isn't it? So what do you think? Does that seem to be a valid way to figure out what the number would be? It feels pretty good, doesn't it? So let's take it and we're going to apply it to 877, do the same thing, and see what that equals. So I'm going to take 877, because that's for number 5, times 0.22951, and see what that turns out to be as a whole number. What do we get? Nicole? 203? Did you use the same digits? 877 times 0.22951? It should come in to be about 201. 201, all right. And so there is my answer, but that's how I did it. So what I did was I wanted something consistent. So in this way, if the data is not consistent, a percentage is a good way to go. Probably some kind of multiplier. So we did that and we tested it out on 3 different parts. That was how we knew for sure that we were on the right track. 3 test subjects is a good idea. And then we applied it to the last piece of data to get the answer. All right, let's try this. We're going to answer these questions. It says, make a conjecture from each scenario. So remember, a conjecture is just, well, the observation that we're making or the assumption that we're making. Do we know it's a fact? No. But based on what the statement says, what do we think would happen? So number 7, every dog you've met chases a squirrel. Every time you see a dog, it is chasing a squirrel. What can we assume?
Dogs like squirrels.
All dogs chase squirrels. Would I agree? Would you agree? If that's all I've ever seen, would I assume that all dogs chase squirrels? Number 8. All children at the summer camp love to play with blocks. So I'm working at a summer camp. All the kids like to play with blocks. What do I assume? Can I assume? It doesn't matter where you are. All kids like blocks. Yes? And number 9. What do I know about the cube of a negative number? What would I assume if I'm cubing a negative number? So we might take and make some examples. If I have -1 cubed, that's -1 times -1 times times negative 1. What would I assume would be what would happen? It's going to be what? It's always going to be negative. A negative times a negative is a positive. And then times another negative is a negative. So this would be negative 1. If I took negative 2 cubed, do I still have a negative? Yeah, it would be negative 8. Negative 5 cubed. Still a negative because it's a negative times a negative times a negative. It's just a negative 125. So my assumption would be it's always negative. Number 10, the sum of two odd numbers. What happens if I add a couple of odd numbers together? Look. Let's try it. Give me a couple odd numbers.
3 plus 3.
5 plus 7 is 12.
3 plus
3 plus 3 is 6. Give me two more odd numbers. What? Okay, let's mix it up. Let's give it a different pattern. Let's do 2 digits. Let's do 13 and
5.
5. 13 and 5 is 18. What do we notice about all of the answers?
They all come
Even. So I'm going to assume always even. The next group. For each conjecture, test with 3 examples or find a counterexample to prove it is false. All right, in 11, so these are already conjectures. We're not making a new statement based on it. All shapes with right angles are rectangles. Do you think that is true or false? Katie. Why do you say it's false? Okay, but a square is a rectangle, technically. Do you have another example? Okay. I think you could run with that. Should we come back? Audrey? How about a right triangle? Yeah, does it have a right angle? Okay. Could draw it there if I wanted to. A right triangle has a right angle. All right, that's a counter example. 12. Any 3 points can be connected to form a triangle. Shelby? That is false. Why do you say it's false? I love it. What if your 3 points are in a line? So I have one here, and one here, and one here. And that's 3. I can connect them, but that's 3 collinear points, right? 3 collinear. Collinear points do not, if I can write all the words, do not form a triangle. Okay, number 13. Any integer multiplied by 4 is divisible by 2. Do you think that's true or false? If I take an integer and I multiply it by 4, yes, Maddox?
Could you inform me of what an integer
I can't inform you what an integer is. An integer is just a number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it's negatives. No decimals, no fractions. Okay, positive and negative whole numbers. Gentry?
True, because 4 can be divided by 2.
Love where you're going with that. So if we take an integer, whatever that is, let's say it's 3 times 4 and divide it by 2. We can automatically divide 4 by 2, can't we? And get 6. So because we can divide 4 by 2, any product with the 4 will also be divisible by 2. So it said it wants us to give 3 examples if we think it's true. Another one would be 17 times 4 over 2. Well, again, divisible by 2, that is 34. Hi. Oh, okay, thanks.
Yeah.
Just have a seat.
Okay, sure.
9 times 4 divided by 2 is 18. So it's going to work out. Number 4. If 2 angles are supplementary, what does it mean to be supplementary, Nicole?
2 angles that add up to 180.
That was the perfect definition. 2 angles that add up or have a sum of 180 degrees. Then one of the angles is acute. If I have 2 angles that add up to a 180, does one of them have to be acute? Yes or no? I called you Audrey. Katie.
You can have 2 right angles.
You can have 2 right angles, and they would be supplementary. So it could look something like this, couldn't it? That's a linear pair. So they're adjacent, they're supplementary, they add up to 180, but they're both right angles, so that's a good one. Anybody have any questions?